Here we are. We are live. Another great week. Another good weekend. Had some fun moving sheep around this weekend. It's always nice when they cooperate, especially in the beginning when you've got them corn trained, and then uh, sometimes moving them back though. By the time you've got them in the pens, you've worked them, and now you got to go put them back. It tends to go less smooth because now they're not so interested. Then you got to actually like drive them where they need to go. And if you don't know what that means, so in the agricultural land, we like when you drive a herd, you're physically like herding them like you'd see in the movies, right? So if you just hear that term and maybe you're not familiar with that, that's what I'm saying. It went pretty smoothly. We had a good count. Only one of the lambs this year so far has had an infection on the face, so just part of the process. Anyway, we're here to talk about chillers. This is not a farming or agricultural show, I guess. Would we call this a show? I don't know if I'd call this a show. This is a hangout session for some Q&As and talking chillers. That's what this is. I do see you there, Dean. York Titan. OM Chiller. Titan. I'm trying to think. The Titan. I'll look that up real quick. York Titan Chiller. What am I missing there? Yes, okay. That's their larger line of their custom centrifugals. So that's where you start getting into there's a lot of really interesting setups. Yeah, you said the OM, yeah. Yeah, I mean, it's one. What can I explain? The Titan series for their OM series, like it's really these are machines purpose built for that particular site. So one of the things that's different about chillers in general, especially when you start getting into the centrifugal side of things, they typically are spec designed for that site. So we'll take a YK as an example. A YK has a general design and a set of options or features that you can have added to that chiller, right? So we could have hot gas bypass added. At one time, VGDs were an option, even though I think that's standard now. I could be wrong on that, but so those were options, right? An option could be, do you want a VSD drive, unit mounted, floor mounted? Those are options. But the flow rates, the tonnage, the compressor that gets used, the lift that is expected, or we're expecting a high lift scenario, that's going to affect which way we go with the compressor, which heat exchanger selection we might want to choose, how many tubes we have. All of that is very configurable, but it is in call it a predetermined package. Then you get into systems like the OM series, where, from my understanding, now I'm not overly read up on these, okay, so I'm not the best person to ask about those, but York will genuinely design machines. They'll take the basic principles of just how York designs things from a general standpoint. They'll take all of that, but then they will truly make it exactly what your site needs. And this is where you start getting into industrial manufacturing, especially like major process systems, maybe low temp systems where we're trying to chill down into the negatives of degrees in some cases. And I mean that in Fahrenheit. So I'm not even talking about Celsius there. So it would be really difficult for me to give a really good explanation on an OM series without just knowing a lot about your site, a lot about your machine, what it was designed and spec'd for. And maybe, how about this? This may be a good point. Because I don't have a lot of background with the OM series. Why don't I take some time this week, put some time into it, read up on it. Maybe there's some more consistency between how they do some of their designs than I think there is. From my understanding, it's quite different between machines, but maybe I'm wrong. And I'm sure they use a general format of, okay, we're going to start here and then we'll configure from there. And if we have any JCI guys jump in the chat, feel free to kind of share some of your thoughts or what training you've had on the OM. Maybe I'm totally off base here. My point being, let me spend some time on it this week. And maybe we follow back up on that question next week. And I may have some better feedback. Actually, we can't do it next week because next week I'll be doing a live class. I'm actually glad that came up then. Next week there won't be a stream, so I guess I mean the week after. Next week, so starting Monday, is our first day of the first hands-on class that I'll be conducting and continuing moving forward. So if you didn't get signed up for this one, it's okay. It was a little bit of a short notice. It took a while to get some details worked out. But now that we have all this kind of figured out, I'm going to be doing these routinely moving forward. So I do plan to host another set of classes in March and April. And I do want to give some big thank yous out to a handful of people who've really made this possible. So first is going to be CSG, as Compressor Solutions Group, based out of Houston, Texas. That's where we're going to be hosting this class. So it's going to be at their screw remanufacturing shop. They've got a brand new conference room they just built. We're going to get in there, spend a couple of days talking through things in class. We're going to have some compressors we can put hands on, including a turbo core. And then we're going to go spend a couple of days in lab. And this is also in partnership with SAMI AI Systems. So SAMI is one of CSG's monitoring systems that they've produced. They actually just won the AHR 25 award. That's going to be in Vegas, or I guess that's AHR 26, I'm sorry. Anyway, they just won that innovation award for AHR, which is really freaking awesome. And SAMI is a really neat program. And I say program, so it's this small little module package that you can just put on a machine. I have an interview I did with Justin, who is their president of CSG and SAMI. I highly recommend go check that out. You can hear a little bit more about what SAMI is, how it can be applied, what all we're looking at. And they've really been perfecting SAMI on these smaller tonnage systems, but having that discussion with them about, okay, how do we scale this into centrifugals? How do we add the sensors we need? How do we make this more applicable across the board? Anyway, thank you to CSG and SAMI. I also have a couple of thank yous to give out. One to Navic. So I'm repping their shirt today. Been working with Navic for a long time. Navic has supplied a lot of the hands-on, or the tools and equipment. So we've got, I've got actually right here beside me, I've got a couple of brand new NRDC 4Ms by Navic. That's their 4-cylinder recovery machine, and it is by far, outside of RefTech, my favorite recovery machine I've ever gotten to use. And the subcooler they've got built into these is freaking phenomenal. So we're going to be using those. We're going to have multiple stations set up to practice doing push-pull recoveries, push-pull charging, just transfer in general. I'm going to be working on moisture cleanup in the refrigerant, oil separation from a recovered system. How do we separate that oil out of there? All that's going to be in there. So thank you to Navic for helping supply those tools and equipment and just being a great partner over the years. We've been working together for quite some time now. Really enjoy working with the Navic team. And then we've got AGAS. So AGAS is supplying the refrigerant for this training. They're going to come give us a handful of tanks with some 134A, and we're going to actively practice getting to transfer that refrigerant between tanks and putting all this hands-on to work, and everything we're discussing in class, finding a way to actually apply it into the lab. It's going to be a really, really fun time, and I really appreciate all the partners who have come together and to make that class possible. So next week, I will be, call it out of pocket. We won't be able to do a stream because this time next week we'll be heels deep into into our hands-on class. So I'm very excited for that, and everybody that's going to get to join. Um, it's really fun about that. This is a fun story, and I'll just I'll share real quick, and then we'll jump into the questions here. So I got into professional teaching relatively early on, and basically after I graduated trade school, and I had already been in the industrial side by that point. So I was working on a lot of centrifugals by then. And keep in mind, I didn't go to trade school first, then get into the trade. I spent a few years in the trade, then got into trade school taking night classes while I was still working as a service tech during the day. And so I taught a night class the year after I graduated, and it was just an intro to residential class. So just intro to residential systems. So talking about homes, splits, that kind of stuff. And what's really cool to me, one of the students I had in that class, I won't say his name, but he was actually one of my really good students in the class, and I really connected with him there. And fast forward some, when I moved from East Texas to Central Texas, he ended up following me about a year later. He came down, so he finished the program, graduated, and then I convinced him to come to Central Texas and start off as a Tech 1 apprentice with the company I was with, at the time, start building his way up. Fast forward now many years. I mean, it's been what? Oh man, been a long time. Fast forward many years, and he is now getting much deeper into the chiller side himself, and has come up fully on the heavy commercial side of things, done a lot of work, got really into boilers for a time, and is now getting into the chiller side. And he will also be attending this class, right? So he's going to be one of the guys that's going to be there as part of this hands-on class in Houston. And it's just really exciting and really full circle interesting. And it's something I was telling him about the other day, because he was there in my very first actually professional teaching scenario at the college. And then now this will be my first hands-on public class. And I've done some private sessions, and I've traveled and done some of that for different companies, but this is a genuine public class that anybody could sign up for and come to. And he's going to be there. It's just a really fun, really cool full circle. It's been a hell of a journey, guys. I tell you, it's been a lot of ups and downs to get here, but yeah, it's just those little moments, those little wins. They're important. Anyway, story time's over. Let's get into questions. Keyboard will work. There we go. All right, so this came through the CQA, the Chiller Questions Answered portal at chilleracademy.com. So if you want to get your questions prioritized or follow up on any previous material, that's the best place to do that. It's completely free to log into the portal. This is the only question we have from the portal today, and then we'll dive straight into the questions in the chat and go from there. With that, what is the most efficient way to charge a low pressure chiller? Really, so low pressure. Let's start off with some very quick basics here, just so that we can keep everybody up to speed. When we say low pressure, we're talking about it operates below atmosphere. Okay? So that is a low pressure refrigerant. ATMO. So the refrigerant itself in operation is below atmosphere, especially in the evaporator. So sometimes on these, the condenser side can increase in pressure and get a little bit above atmosphere. All right, so you may have 2, 3, 4, 5 psi in some cases. It also depends on the refrigerant. So these refrigerants are like R11 or 123 or what is it, 514, and And then we have 1230. That's, there we go. 1233 is another one. And then we have what, the 1234 YZD or YEZ or whatever the hell it is that York's using. Anyway, these are some examples of low pressure. Now, one of the weird things about this is because it at its standing, it is below atmosphere. So at ambient, many times our pressure is actually in a vacuum. This chiller sits in a vacuum and makes it very easy to draw non-condensables or just atmosphere into the refrigerant, which is going to contaminate it, cause a whole slew of problems. So the most efficient way to transfer this refrigerant is going to be a push-pull setup. Okay, so to do a push-pull, we've got our chiller. Okay, we're going to say CH. What we'll end up having is our recovery cylinder. Whatever size, it doesn't really matter. But we want to make sure that it's a proper recovery cylinder with 2 valves. So we have a liquid dip tube and a vapor. And we're going to have our recovery machine. It doesn't matter if you're using the Navec, RefTech, that part's irrelevant. What is important is we're going to pull from the, here, let's do it this way. We're going to pull liquid from the bottom of the chiller. Now, typically, these low pressure machines are, I say typically as if they're not, they're centrifugals. All of them that I'm aware of on the market that I've ever seen, ever heard about, they're centrifugals. And with these particular designs, specifically being water-cooled machines, you're going to have majority of the refrigerant in the evaporator once it shuts down. That refrigerant goes into the evaporator and stacks there in most cases. And there's also going to be a liquid charging valve or connection to connect to in order to either recover or add the refrigerant back into the machine. So keep that in mind, is we're going to connect to that liquid port, and which is going to tap us right into the bottom of the evaporator. And we're going to bring that into the liquid port of our recovery tank. It's really good if we, say, have like a sight glass here. That way you can actually see that liquid transferring. Then we're going to be pulling vapor back off of this tank and into our recovery machine. So this process, what we're doing, this recovery machine is drawing pressure down on this tank. As this tank draws down, it naturally wants to siphon refrigerant back into the tank. Now, we have to send the vapor we're pulling off somewhere. It can't just sit in the recovery machine. So we're going to come out of the recovery machine and then back up into a vapor port. So I usually, like a lot of these machines, they'll have a large service port right off of the suction elbow. That's a great place to connect to. You could also just hook it up to the top of the evaporator. Either way, this is a basic, actually the question was charging. I just showed you for recovery. This is a basic push-pull recovery configuration, not for charging. Okay. For charging, I'm sorry. We're going to flip this the other way around. I don't need to change any of the colors here. We'll just point it the other way. So in a charging scenario, all of our refrigerant is in this cylinder. We want to get the refrigerant out of this cylinder into the chiller. We're going to connect the exact same way. We're going to have our inlet to the recovery machine come off of a vapor port. Like I said, that suction elbow port, something like that, is always really handy. Okay, so we're going to flow this way. We're going to be drawing into the recovery machine. And we're going to push that vapor out of the recovery machine and into our recovery cylinder. That recovery cylinder is then going to allow that vapor to push in on the vapor port and draw out, or push out, I should say, into the liquid charging port of the chiller. Now we may have multiple tanks, we may just have one really big large tank that's able to hold the whole charge. Either the way, this is the basic flow. And so what's happening is twofold. One, we're drawing vapor off of the chiller. Drawing that vapor off lowers the pressure in the chiller, which naturally makes the liquid refrigerant want to siphon. But we're then pushing that vapor into the cylinder itself. Pushing that vapor into the cylinder is going to then naturally want to push that liquid refrigerant out of the cylinder. And that's where the whole concept of push and pull comes from. We're pulling with this line, pulling off of the machine, and we're pushing with the vapor in the tank into the machine. And it, like, the speed of this compared to other methods is just crazy. If you're trying to do a standard charging or a standard recovery, anything like that on a machine like this, just doesn't make sense. Even if you have small hoses, it doesn't really matter what your setup ends up being. It is ideal to have a proper recovery machine, like a RefTech machine. It is ideal to have large diameter hoses. Like, all of that becomes really, really recommended, important, something along those lines. But however the process you use, if we tried to do like a vapor charge, right? So that's one way to do this. Then trying to boil off, especially a low pressure refrigerant, it's already at such a low pressure, you got to draw that tank down and boil all that refrigerant out. It's just not feasible, right? And then you could do a liquid pump transfer, right? So that would be one technical method. You could try to hook up a pump and then just pump the liquid, whether it be through a recovery machine that's rated for that, like the Navic machines. You can move liquid through those. Or if you use a literal liquid pump. So they have liquid pumps on the market where they're not going to do anything for your vapor side, but they will transfer the liquid in between. So that is options. But I've tested a lot of these options, and it is not faster than the push-pull. Ultimately, the push-pull is your fastest process to get refrigerant from the tank into the machine and vice versa. Some key notes here. It is recommended, especially if you're wanting to do this like by the book, to vapor charge your machine before you start putting the refrigerant in. So some things that should be true if you're ready to charge refrigerant. You should have already pressure tested the machine and it held. You should have already pulled an evacuation on the machine and it held. On a machine like this, when we're talking about these centrifugals, we're talking 24 to 72 hour pressure tests. We're talking a 24 to 72 hour standing evacuation or vacuum test. Or after you complete the evacuation and you get it down to below that 500 microns, then you stop. You'll walk away and you make sure it holds for the next 24 hours at least. That's what we're discussing. All that should be assumed on my part that you've already done that piece before we're even trying to transfer. So if that be true, before I even hook my hoses up like this, I'm just going to run my vapor line over and pre-charge the chiller with vapor to get us above a freezing saturation. So what pressure does that mean? We could pull up our ref tool. So let's go with a 123 machine. And we want to get above, let's say 35 degrees of saturation. Now this is in gauge. So my gauge pressure would need to read basically negative 10 psi. So from 500 microns to negative 10 psi, I have now crossed over 35 degrees of saturation for this refrigerant. All right, I don't know if you can see that, but now if we're going off of absolute, then it would be 5 psi A, not G. All right, so that's absolute pressure, but most of the time we're operating in a psi G context, or at least I do. And so negative 10 psig. Once I got the cylinder to that pressure with our vapor first, then my concerns about freezing the water go way down. And you could even take it to 40 psi or 40 degrees of saturation, which, okay, what does that mean? So 40 degrees would be basically negative 9 psig. So if we took it to 40 degrees of saturation, like the concern, so we get into concerns about freezing tubes when our refrigerant saturation is below freezing and we have liquid make contact with the tubes, which will happen in the evaporator. So as you're pumping this liquid in, you will start to have liquid make contact with the tubes in the evap. If that liquid refrigerant is below freezing temperatures, you run the risk of freezing those tubes. A frozen tube will rupture and give you just wreck your entire day, your week, your month, probably your year, because then you're talking about a retube or at least plugging that tube. It's a mess, and then you've got to clean all the water out of the machine, out of the refrigerant. It becomes a disaster. So we don't want to do that. So pre-charging, and this doesn't negate needing to flow refrigerant. I still push that you don't want to flow water. You don't want to flow water during your pressure test. You don't want to flow water during repairs. You don't want to flow water during evacuation. Have that water isolated and not moving. But when you get to the point of needing to charge, then, and this is true for recovery, then you turn the pumps on or open the isolation valve, get water moving through the machine. Protect your tubes. Pre-charging with vapor only helps protect the tubes further. It's crazy how expensive it is to try to fix and clean up a flooded machine. Let's just not do that, okay? Anyway, so back to the core premise of our question. What is the most efficient way to charge a low pressure chiller? That is going to be the push-pull method here. Pulling vapor, pushing that vapor into our recovery cylinder. The lower pressure in the chiller draws the liquid in. The higher pressure in the cylinder pushes liquid in. They both work in unison, moves a lot of refrigerant really fast. There are other methods to this, by the way. So one would be what's known as a gravity feed. And I've done this. And so if you, a lot of your low pressure refrigerants will come in drums. They won't be a recovery cylinder. Like if you buy 134A, you're going to get it in a cylinder like this. But you may buy a drum of 123, and it comes in a literal drum, like a oil barrel, usually smaller size, like in a 100-pound increment or something. And the way that, like, just the way you get that refrigerant from A to B is you put an adapter on the tank, but then you just hold it up and you gravity feed that refrigerant into the chiller. So that is a method. So hooking, or you can set it up to where if your refrigerant is in a recovery cylinder, instead of trying to use a machine or anything to push that refrigerant over, you could just hook up to the liquid line, hoist that tank in the air. You have to flip it over, so keep that in mind. You have to flip that tank over, and you're going to hook up. If I said liquid line, I made a mistake. I meant to say vapor port. You're going to hook up to the vapor port of that cylinder, flip it, and then hold that cylinder up above the evaporator. And you don't have to go literally above just where the liquid level line is for the evap, which is about halfway. So as long as you're above that, that liquid refrigerant will drain. It won't do anything for your vapor, but it will drain that liquid charge into the machine. If I'm charging the drums of refrigerant, I'm fine with that. Like, it's just the way we do it, at least the way I've been shown to do it. But when we start getting into these larger cylinders, especially once you cross over that 240s into 1,000-pound cylinders, I'm not doing that. So hence push-pull. That is our solution. Good to see everybody in the chat. I see you, Brad. I see you, Ram. How you doing, Sterling? We got Tom himself. Looking forward to seeing you in Houston, Tom. And then Mr. Joshua. All right, let's dive into some of these questions. I see, what do we have here, Brad? Do you have a specific procedure for major PMs on centrifugals, beginning to end? Yes, it does kind of shift depending on the chiller. Let's all right. Yeah, we'll get back to that, Sterling. Yeah, Carrier is. I don't appreciate their thought process many times. Okay. So, what is the most efficient? That's not. Hang on. What happened here? Oh, I know what I did. My bad, everybody. Just give me a second. One of my programs where I can customize my mouse is not working today. And my muscle memory was trying to use my mouse. Because I've got customizable buttons. I can do a copy paste kind of thing real quick and easy. But not today. All right. Do you have specific procedures for major PMs on centrifugal chillers, beginning to end? Yes. So I would look at it in more of I have a flow that I like to do. And there is a difference in, I'll take it from a basic PM standpoint, and we still have a difference between low pressure and high pressure. So there's a very specific step that gets added with low pressure machines, which is where we have to pressurize the machine. And keep in mind, low pressure operates below atmosphere. So we're in a vacuum, and if we're going to do a leak search, then we need to get the machine above that vacuum. That means that, or above atmosphere. That means that we have to pressurize it to at least 5 to 8 psi is pretty typical. I really don't recommend pushing up to 10 or more, because 15 is when you start rupturing burst discs and just bad things start to happen. So 5 to 8 psi is pretty normal for pressurizing a low pressure machine. A lot of things for me do kind of scale across the different, like from low pressure to high pressure. It's still the basic kind of flow. Excuse me. And so I'll kind of talk about that, and we can draw that out here as to what that flow for me looks like. But there'll be I just want to put the caveat in there that when it comes to low pressure, we have to add pressurizing. I'm taking this from a major PM, so we're talking annuals, right? We're doing a complete top to bottom, so we have to add pressurizing the machine and purge service. So servicing the purge system, purge dryer, that kind of stuff. It needs to be accounted for when we're discussing this process. And then everything else would be just your basic high pressure, right? So the low pressure adds steps to the process. What I like to do, and my preference, okay, this may be a good follow-up question. Do you want me to take an approach of a one-man team or a two-man team? Because my preference is to do a two-man team on this process. But we can take it from a one-man team standpoint. Okay, so you're most interested in the CVH series. Okay, so you want to see, okay, what do we do for a low pressure CVH centrifugal maintenance? I tell you what, I'll draw out my ideal scenario, and then we can 2-man annual. Perfect. All right, that is my ideal. We get to the site. One of the very first things I want to do, we're going to go ahead and do a shutdown. Okay. From there, we're going to fork off into two things. One tech is going to start prepping two brush tubes. The other tech is going to, oh, that's not going to work. The other tech is going to start working on electrical connections. So doing electrical checks, servicing the purge. So the purge filter, checking the purge sensors. So a purge service. And then, 1 second, guys.
The yellow scale is the one I was talking about. Is that one broke?
Yeah. Yeah, we have to use that one.
Is it the same operating?
Yeah, just turn it on.
All right.
With electrical checks, purge checks, and then let's see, what else would I have them do? We can verify sensors and stuff at the same time. So while it's not ideal, most of the time it is best to verify sensors at operating temperatures. I've found that in most scenarios it's actually okay. If there's a major issue with a sensor, we can check it at standing and we'll call it good enough, right? So we could debate that to nauseum if we wanted. Anyway, checking sensors. All right, so one tech's on the electrical. So when I say electrical, what I mean is going into the control cabinet, tightening all the electrical, and making sure that we don't have any burnt wires, we don't have anything loose. All the connections are good and tight. We're happy with everything. Then going into the drive and starter panel, whatever the case may be, servicing the starters, servicing all the connections. With a low pressure, you're not going to be megging the motor at this point. You're still in a vacuum. You have to wait until you do the pressurization for that. So yeah, cleaning the starter contacts, making sure the starters are in good shape, all the major electricals in good shape. If we have a drive system, going in and servicing the drive, again, doing any checks we need. Those are refrigerant cooled drives, so we don't have anything on the drive cooling to really worry about, except for the air cooled drives. Those we need to have the little filters and stuff checked, make sure the fans are doing okay, then none of them are locked up. So when I say electrical, that's what I'm referencing, is the controls and starter panels, really going through those in detail. And I am one that trains on, we touch every terminal. Every terminal should be checked for its tightness, its connection, nothing's loose. We don't have a wire that's getting hot and kind of maybe wiggling out of its terminal point, anything of that nature. None of that should be happening. Yeah, electrical, and then purge. So by purge, I'm talking we're going to service the filter. Some cases, the customer may want to change out the purge valves, so the pump out valves specifically, during a annual. That is, whether you do it annually or you do it on like a 3 to 5 year cycle, it is recommended to do that because those pump out valves go bad so frequently on those machines. They cause a lot of nuisance non-condensable issues. I know Train, local to me, like that is their standard procedure. They go in to do a maintenance on these as part of their annuals, at least that's my understanding. They're going to change those solenoid valves out entirely, not the coil, but the actual valve. So that may be something that this person can be working on in that process. And then, yeah, verifying your sensors, all your temperature sensors, your pressure sensors, which depending on your vintage of your CVH, newer machines do have a high pressure transducer. It's usually located inside of the purge cabinet. But if it's an older machine, you may just, there may not be any, well, you would still have the oil pressure transducer. You just may not have a refrigerant pressure transducers on like the high or low side. So that's going to depend on the vintage of your chiller at the time. Anyway, all that is happening while this guy's brushing tubes. So this part here, depending on the size of your machine, this may take a day, this may take 3 days. So it's just a lot of work goes into brushing a machine. And usually if this guy needs whatever he needs help with, setting up to rig the end bells, setting up the tube brush machine, if they don't have enough brushes while they're on site, this guy here doing this job is supporting the tech that's brushing tubes. This is a not fun, nasty, dirty, just suck job. None of us enjoy it. It is what it is. Well, I say that. The guys I've seen that do enjoy it are huge podcast just fanatics, and this is their prime podcast time. They throw earbuds in, they go podcasting, and they brush their little hearts out. More power to them. I ain't one of those guys. I do enjoy podcasts, but I ain't one of those guys. Anyway, so yes, this guy's supporting him. Once this is done and the tube brushing is done, then we can get into a pressurization. So, and quick pause here. I'm taking this from a normal annual. I'm not taking this from, you did say a major. Okay. Every 3 to 5 years, we should be opening the evaporator and checking eddy currents. Right? So if we're talking major as in we're going to eddy current, then in this brushing tubes process, this will be more than just the condenser. This would get done on both condenser and evaporator. I'll usually start with the condenser, get it done, then do the evaporator. So if we're going to do an eddy current, that's where this comes in. So we'll have an eddy current tech come in and process both sets of tubes. If whatever the condition may be, if we've got to plug tubes, whatever the case, we'll handle that at this point. We'll do that while he's there. Identify those tubes. If he does have a set of tubes he wants to plug or he recommends plugging, then we have to go through the process of opening up both ends of the barrel, which, most scenarios we don't need to do. But in this particular one, like if we got to plug a tube, we got to get to both sides. So working through that process of getting this eddy current piece of it done. When eddy current is done and we're wrapped up with that, then we can move into pressurization. So we want to pressurize and leak search. So pressure and leak. So brush tubes, eddy current, pressurize and leak search. This guy who's focusing on all this stuff, he's got plenty of time to do this stuff correctly, by the way. As all this is happening and he's helping support, he has plenty of time to go through this. That's one reason why this is where so many of our issues lie. So many of our issues. And so I am very meticulous with this process of take your time. Don't rush. And if we're doing a 2-man process, don't rush. If this was a 1-man process, basically I usually insert this down later into the workflow. So I'll start with tubes, eddy current, pressurizing and leak search, and then after we do the leak search, then I would probably do the electrical purge and sensors. Right, that would be a good time to do that after we finish the leak search process. If I was doing this by myself. Okay, so pressurizing leak search. While we're pressurized, we also need to megohm. Okay, megohm the motor. Meg. We don't want to do this while it's in a vacuum. We want to do this when it's in positive pressure. When we do the leak searching, this is the time to do your megohm readings. That's where this guy over here comes in. This guy is setting up the pressurizer, getting it going. Once we're up to pressure, like, this is where you get involved. Let's see. This is also a good time to, so this is a good time to do the oil filter. So take another branch, oil filter, and sample. Again, while we're pressurized, you don't have to do it while pressurized. This can technically get done later. It's just a really good time to do it so that you limit the non-condensables that get drawn in. Again, depending on if you're pressurizing at all. If you're not pressurizing, let me take it from that standpoint, you're not going to get a successful leak search. Like, there's just no point in trying if you're not able to pressurize. I don't care what method you use for pressurizing, whether it's hot water out of the tap, whether it's using an actual pressurizing machine. I don't care what method you use. Try to pressurize. If you can't pressurize, you're not going to be able to properly get a leak search. Just not going to happen. So you're just, at that point, you're solely relying on your purge unit being able to give you feedback on the pump outs and trusting the purge to actually be working correctly and all that stuff. If you have a machine that's having major surging issues, like, you just, even if the purge says it's not a non-condensables problem, you just really should just pressurize. Anyway, so if we're not going to do this, then we're not going to get to Meg. Just don't do it. And when you do the oil filter service, it's just going to be, you're just going to have to deal with the non-condensables to get drawn in. It just is what it is. Usually I'll turn the pump on, and this is one issue with this method. To get your oil sample, you're taking the oil sample from the output of the pump, which is not ideal. It is best to get the oil sample at the bottom of the sump. That is what is ideal. That is best. It's not always possible. It is what it is. But when we can, if you're pressurized, get that sample from the bottom of the reservoir, or the tank as Trane would refer to it. Okay, so electrical's done. We have our eddy current. We've pressurized. Oil system serviced. We've megohmed. We've verified whatever leaks we're going to deal with. Yeah, then we get into ops. So bring the machine back on. We do an ops check. So by this time, I know that all my sensors are accurate. I know that everything electrically is good. I know where my refrigerant systems conditions are, so I'm checking. Like, this is where I'm logging the machine. It's the very last step of this process for me, doing a complete log. I want all this done before I go to log it, because I'm already there to do the service. So to me, if it doesn't hurt if you want to do a preliminary log and do a before and after log. It's not a bad idea. If you have time for that, if you're worried about that, if the machine maybe is having issues and you're trying to see, is this maintenance going to help with said problem, that's not a bad idea. As a standard, though, of just, this is my general process, I'm really not too worried about what the conditions were pre-maintenance. I want to know what happens when I'm done with my maintenance. That's what really like matters to me. Um, One thing, like when you're doing this purge, make sure you pull an evacuation on the purge lines. Now, I'm guilty of this, getting lazy and just opening the lines back up, letting the purge deal with the non-condensables that got introduced while changing the filter out. I get it. I've done it. It is best to, like, if we can limit the amount of non-condensables, the better off we're going to be. That's why we're going to do the oil filter while pressurized. And then we can do the purge while it's still in a vacuum. That's not a problem. We have to isolate the purge, right? So close the isolation valves, go into the purge unit, then do your purge filter, then pull an evacuation on those lines. Most systems should have a 1/4-inch tap that you can hook even just a small, fast little vacuum pump to. You're not trying to pull it down to 500, right? We're just trying to get all the non-condensables that they got drawn in during the maintenance process back out of there. That's the main point. Just do that. Yeah, so that's the overall for a CVH, right? So let's make sure we're on the same page there. This is for a CVH machine. Okay, or just a CV, a trained CV chiller. Marker's leaving it open too long. That's the process we're going to go through for one of these trains. Or that's the process I'm going to go through in just kind of a workflow. Now, just getting back to the core of the question, I have a specific major PMs. Any specific, so I talked about a lot of those procedures in this kind of workflow of what I'm going to do in what stage. Like, okay, this is what I want to do while pressurized, while the tubes are getting brushed. This is what one tech can do while the other tech's working brushing. Yeah, I think I covered just all the little nuances, at least that comes to mind sitting here. You know, there may be some other small things that if I was standing in front of one might pop in my brain in the moment, but yeah, that's my general workflow on that. It's a really good question. Really good question. Staging sequence on a primary secondary loop. Let's do it. Yeah, and just keep in mind, this Q&A chat is more than just strictly the chillers. So if you have plant controls, questions, things like that, feel free to share them. Obviously, some questions may be harder to answer than others, and I'll just tell you if they are. That's okay. But at least ask them now. That's not going to work out. I'm going to come from here. And right there. Perfect. Okay. Can you explain staging sequence in primary, secondary loops? So let's show what that means. And we're talking about a chill water loop here. We could, we won't complicate it. Talking about a chill water loop for whatever facility we have. And this is a very common configuration. So we're going to have, let's just say we have 2 chillers here. Okay. Chiller 1. Actually, I'm going to need more space than that. Chiller 1 and chiller 2. So our first set of pumps is our primary pumps. So we want to push into our chiller. Okay. These are the proper symbols for a pump, by the way. So if you're ever reviewing a schematic, they're going to be this circle with a triangle. Now, in some cases, you may see them, they kind of visually represent in more of a pictorial fashion a centrifugal water pump. But in terms of a like actual schematic symbol, this is your pump's symbol. Okay. So this is typically coming off of a header and will be feeding back to the load. Okay, so, or coming from. All right, so we're flowing this way. And this will be just kind of a blank off, or it could be an elbow there. That I've seen them do it either way. Now, this will leave as chilled water. And we will go to another header with another set of pumps. And we could have however many pumps here. Okay. So here we could say, let's just say this is 55-degree water Fahrenheit coming in. Chillers are ideally outputting, say 45 in this case, just whatever the case may be, it depends on your loop. This is our basic plant layout of what this plant should look like. These are your primaries, these are your secondaries. So they'll be identified as like primary chilled water pump 1. This will be primary chilled water pump 2. And then we'll have our, I've seen it done two ways. It's either S or SEC. We're going to use just S in this case. So S, so secondary chilled water pump 1, and then pump 2, pump 3. So in terms of you're walking through the plant, you're seeing these labels, whether on the starter panel, you've got one, say, large MCC panel, or on the actual pumps themselves, they're labeled. You should see some kind of labeling. It's not always done this way. I've been in plants where this was just pump 1, 2, 3, 4, 5. That's all it was. Nothing else. I've been in plants where it was identified as primary chill water pump, secondary chill water pumps. You had 1 and 2, 1, 2, and 3. That really just comes back to whoever did the labeling on the plant, what they decided, what the original engineers decided to draw up. Usually an engineer will actually identify things, I would say, correctly. And then if the plant's been overhauled by somebody at some point, they may not follow all the same stuff. And that's where you get to, this is just pump 1, 2, 3, 4, 5. Anyway, what's happening here? These pumps serve completely different roles. Oh, there should be a bypass here. Yep. Let me get the bypass. 1 second. Almost forgot that. All right. We're just going to draw a simple valve. Yeah, if you're looking at a schematic and it's got the little stem with those colored in square, this means an actuator. Okay, whatever, and depending on the symbol, that'll change the type of valve, right? This is just not an actual. Well, you could argue, I think this could be a butterfly. Is that right? Butterfly symbol? No, the butterfly is different. Anyway, actuator. So this is a bypass. This is how we regulate the flow on the primary and having the secondary. So these up here, by the way, I didn't draw this. I should have. These up here feed into a header. Okay, and then this header flows out to the load. Okay. Technically, this should be between the header. We're just going to go with it. So the staging process, that was the core premise of the question. How are we going to sequence this plant? So these pumps are dedicated to the chillers. Each chiller has its own set primary pump with a setup like this. These primary pumps, their main focus is not the main loop flow. It is the chiller's flow. And they will be calibrated, whether they're variable speed, however they're configured, they'll be set to at least the minimums of the chiller. At least. When I say minimums, I mean GPM. So we're taking a DP here. We're getting our GPM through the chiller, and then we're going to use that to configure how the drive or the starter, whatever the case may be, for this for the pump to work and function. So the primary's job is to serve water to the chiller itself. That is it. The secondary pump's job is to serve water to the loop, and it's going to take the water from the chiller and push it back out to the load. Now, these could stage however needed. At a really high load state where we've got major demand on the loop, we may need all three pumps. We may only be running one chiller at the time. Okay, so let's say chiller 2 here was our lead chiller. So if we take a lead lag, means one chiller carries the load first, and then the second chiller only turns on if it's needed, right? That would be a lead lag configuration. We could do the same thing on these pumps, just like the chillers. So let's say chiller 2 was in a lead role. It is the main chiller to turn on. We only turn on chiller 1 if chiller 2 cannot maintain control of the loop, which we would see via our return water or our leaving water. We can use these to determine, okay, our load is too high, we need both chillers. So if we only have pump 1 on, or I'm sorry, chiller 1, if we only have chiller 2 on, and we have our primary chill water pump 2 serving that chiller, we could still have a full load and need all three of these secondary pumps to maintain flow through the loop and to get water to all of the load devices, whether that's air handlers, whatever the case. And we're going to monitor this based off of a DP across our loop. So we're going to be measuring differential pressure between the supply and return water, or the plant leaving water and the plant entering water, right? We're going to be monitoring a DP here. And again, this bypass, I'm just going to have to fix it. It's going to bother me too much. This bypass doesn't go from here. It actually goes from up here. So we're going to bypass from this side of the header to the incoming side of the header. That way we can balance our DP. So we're monitoring our DP here. That DP will affect how many secondaries we need on. So as our pressure begins to drop too low, we need to either speed these secondaries up if they're on a drive, or turn more on to get that DP back up. And we're going to be controlling solely based off of that for these secondaries. The more load we have, the more flow is being asked for, the more we need to turn on the secondaries to give that side of the system that flow. And all this will need to turn on simultaneously. We should not be running the primary pumps without having the secondary pumps on. And this is part of where the staging sequence on a plant as a whole, typically, when we're first turning a plant on, whether it be from being off overnight or whatever the case may be, maybe we had a temporary shutdown on the manufacturing line, and we just shut the loop down because we didn't have any load and we need to bring it back up. We'll turn these pumps on usually and establish flow for 10, 20, 30 minutes. and make sure everything balances on the water side before we ever ask the chiller to actually turn on. So the plant control system will turn on the primary and the secondaries together, get the plant stabilized. Even though we're not making set point, it's not the point at that point in time. It's just a matter of get the water stabilized. Then we'll start turning the chiller on and start letting the loop pull down from there once we have the loop stable. Because if we try to turn all these on simultaneously, a lot of weird stuff can happen with the flow and the pressures and trying to stage up and get the loop balanced. It's going to just freak the chiller out to all ends. So that's not a good path. Okay. These are going to stage based off of the loop load. These are just on. They're maintaining flow through the chiller. And as we begin to get lower in load and we don't have as much, at some point we hit a breakover point where our primary loop needs to move less water through it than what our chiller needs as a minimum. So at some point we start actuating this bypass valve so that we are bypassing this water into the supply water leaving the plant into the return water coming back to the plant, so that we can maintain a set GPM. It's not even about temperature control at that point. We need a set GPM, because part of what will happen is if we don't have this bypass, these primary pumps will start really pulling down on the return loop trying to feed the chiller, and then we start choking the chiller of water because we're not able to run, or we're not running enough secondary pumps, but we don't need to, or we can't because we don't have the load to load up that many secondaries, or to get the secondaries to flow that many GPM at the time. So we can use this bypass to then recirculate that loop water so that we can maintain GPM at the chiller, even though we've got less load at our air handlers, let's say. So just to kind of recap on the question, just from a staging sequence perspective on the primary secondary loop, this is what a secondary loop or primary secondary loop will look like, and that is our main staging. So if we want to bring on chiller 1 or 2, these don't really affect what these secondary pumps need to do. They only affect which primary pump we're going to run. So if we wanted to switch over to chiller 1, we're going to bring on primary 1 for that chiller, and we could shut off chiller 2 and primary pump 2. Now keep in mind, the chiller is going to shut off before the pumps. So we're going to shut the chiller off. These pumps need to stay on for several minutes to just let everything in the chiller balance out, stabilize, do what it needs to do. And then we can shut the pump off, which there shouldn't be a case. So normally, if we're having to shut these off, like if we're shutting both of these systems off, both chillers, meaning that both primaries don't need to run, if we're just wanting to recirculate, then we will end up running both sets of pumps, at least one of them, right? We'll at least have the primary pump 1 or something run in conjunction with the secondary pumps in order to have flow. If we want to maintain flow on the main loop but not have the chillers online, like that is something that we will end up doing in that scenario. At least these are from the plants I've seen and that I've worked on. This is the designs I'm familiar with. There may be some other tweaks to this for we run into all kinds of stuff. All of this is engineered, right? None of these are copy paste blueprints from anybody. All of this is spec site engineered. This is part of why it's a applied system. We're actually engineering for this site to meet its specifications and everything around it. Like, this isn't just a package you buy and have brought to you like you can with a regular split system or just a 5-ton RTU, right? Not the same thing there. Those are stationary. Yeah. Let me see, make sure there's not any other questions. Oh, Brad, I'm sorry. I just saw your other your follow up there. Changing the oil, yeah, only if necessary. Uh, some plants, or if your boss, either or, says they want the oil changed, then it's necessary. Or if the condition of the oil is bad enough, then yeah, we're going to change the oil. Bad oil on that, Brad, is going to look like dark. It's got maybe a little bit of an odor to it, but it's going to be a dark color. It's may have some little stuff floating in it. It's going to be really, really thin in viscosity. Now, keep in mind, oil at operating temperature is going to be much thinner than it is at cold. But you can tell when oil begins to break down because it becomes just so, like, it's literally not much more than water. Like, it's so extremely thin as it begins to break down compared to what it would be if it was in a good condition. It would still have some kind of viscosity to it. It'd be thick in some way. It'd be this, as they would say, viscous. Anyway, that's what I'm looking for in that oil. It's also what that oil sample needs to tell me. What kind of condition is that oil in at the time? Things of that nature. Yeah, that's my personal approach to the oil change. Only if actually necessary, if conditions show that it is time for that. If that oil is still and looks really good, is still clear, not really seeing, not really smelling anything weird with it, leave it in there. It'll be good to go. It's fine for probably another year, 6 months, whatever it is between the next maintenance period. By the way, really good question, Tran, on the primary secondary pumps. Hopefully I fully answered that to the extent that you needed. If anybody has any follow-up questions on that, feel free to throw those in. Let's see, chiller, water flow switch, warning. This is my work, Saudi Arabia. Okay, welcome from Saudi Arabia. Yeah, so your chill water flow switch there, Ram, is going to be focused on just one, is the sensor calibrated? So you say flow switch. If we mean a literal paddle switch, one, those routinely go bad all the time. All the time. So if it is a paddle switch, it could be a number of things. It could be here, let me just put this up. Let's keep everybody on the same page. Okay. Chill water flow switch warning problem. Please explain. So if we have a paddle switch, then it could be just the switch itself beginning to go bad. All right, so just a bad switch. Very, very common. It could be a calibration issue. So those paddle switches do have springs to adjust their sensitivity. People mess with them all the time. And so it could be just out of adjustment. So it needs to be calibrated. Needs cal. It could be especially if this is a newer switch or something, you could have they may not have put enough paddles in. So it could be a paddle flex issue. Okay, so when I say paddle flex, these paddle switches come with multiple of the little paddles in there, right? So what you want to do in that scenario is on the back side facing away from the water flow, you want to add those shorter paddles if you're using a longer one on a larger pipe. So you'll have you could have up to 2 or 3 of the supporting paddles on the back side there, giving it more rigidity. Because it is one of the issues you'll run into is these long paddles tend to have a lot of flex. So you don't want that flex. It's just the nature of it's a long paddle. It is what it is. So we have to add those others as a support in order to give it more rigidity so that it will trigger properly. All right, so paddle flex could be an issue. That'd be something to look into. Are those other paddles there? If it's not flex, and it could be a narrow nipple. Didn't think I'd be saying that this morning, did you? So in that case, what ends up happening is it's best to, the bare minimum for these is a 3/4 inch threadlet is what you really should be using. It's even better to do a 1/2 inch. So here's the thing with a 3/4 inch. That needs to be a surface mounted on the pipe. Okay, so if we have our pipe here and we've got a 3/4 inch, but we've got a extension on the nipple or on the threadlet, that paddle sitting in here does not have enough room to flex and trigger. So if it's going to be a 3/4 inch, it has to be down here on the actual pipe surface. That way that paddle has room to flex and move back and forth. Okay. If you are going to need to put it on a nipple to extend the distance for whatever reason, it needs to be a 1 inch size at least. And you could always put a reducer down from 3/4 to 1 inch up here at the threadlet. But that 1 inch is needed in order to have enough swing in the paddle. So if you don't have that so you could just have the threadlet itself or the nipple extension, whatever the case may be you're using, very well could be preventing that paddle from actually making the switch. It might do it sometimes and it might not. That may be where it's being erratic. Yeah. Let's see any others. Switch itself went bad, which would be the electrical switch specifically. It needs calibration. Could be a flex issue on the paddle. Could be a nipple issue. What else could we have? I feel like I should say I'm not a medical professional and this is not medical advice. I don't know why. Maybe I don't know. Dry humor, I'm sorry. Let's see. Yeah, those are going to be the main issues for a paddle. Now, if we're talking electronic, I have to change my marker soon. We have an electronic flow switch. It's very likely a calibration issue. And these have to be calibrated to they're recommended to be calibrated to the minimum flow. So you're going to intentionally put the chiller down to its minimum flow allowed, and you're going to set the flow sensor's trip at that level. Not its maximum, but its trip. So that if we actually get below that point, we trigger the flow sensor. Then from there, anything above that, which if you've got, being electronic, you'll probably have some LED indicators, like you'll get deeper into the green or whatever the case may be. It's just showing that you've got really good strong flow. And then as you have less flow, you're going to see that come down. So when you're calibrating these, it's important to calibrate them correctly. Otherwise, they really don't do you much good, and they're just a useless piece of jewelry for the chiller. It could be a bad sensor, all right? So the sensor itself could be just bad. We may have, so one thing that could be true for both of these, just bad flow. Okay, so if we could have just bad flow, which may be a strainer issue, could be a pump issue, whatever the case may be. We could just have bad flow, by the way. Like in all of this, we may check your strainers, check your valves, make sure your pump is actually moving water the way that it needs to. Okay, so back to electronic flow. Could be a calibration, could be a bad sensor, could be bad wiring. So the harness itself could have an issue. They run into that sometimes, and it's not even a sensor problem. Even though you think it is, you put a new sensor in, still having the same problem. And it could be just the wiring itself is causing you issues. So calibration, sensor, wiring problem. Those are going to be the main things I'm looking for with an electronic. And a DP sensor, so if you're measuring differential pressure for this, that could be calibration on the transducers. That could be a set point issue. Maybe the set point isn't configured correctly on the DP sensor control. Or you could, the pressure taps where the transducers go on to plug up all the time, which is why I hate DP sensors, or one of the reasons I do, is the pressure taps just get full of crap. Even on a closed loop chill water loop, they get full of crap, and these transducer no longer reads accurately, and it just causes all kinds of chaos. And so, yeah, that goes back to, or if you have a DP sensor for a flow switch or a flow sensor, that's what I would be trying to pay attention to. I think those are the main things I'm trying to watch for. Primary issues on the paddle switch. The main stuff I'm going to be checking for an electronic. It could just be a genuine flow problem. Or if we have a DP sensor, then I'm looking to look at, okay, what is the actual set point for my DP on this flow sensor? Is that even correct? It may not be. Are the transducers able to actually read pressure properly? That could be an issue. So take the transducers out. Are the ports actually open? Are the transducers reading correctly? A lot of those DP sensors, you can actually, you'll either have a reference chart or they'll have a little display on them where you can read the pressure that it sees. You know, one of those options is typically true. So you can read the reference feedback from the transducer to the controller to see, okay, it's this VDC coming into the controller means X pressure from the transducer. Is that correct? If you compare that to a calibrated gauge. And then, let's see. Yeah, if it's not correct, then is it the transducer or is it the port itself is plugged up? You need to clean the port, and then the transducer will suddenly start working just fine. Yeah, all right, that wraps up that one. Whew. Insufficient paddle switch. Stop body shaming. I know. I'm sorry. I'm terrible. I can't help it you have narrow nipples, okay? That's not my problem. I didn't create that. I didn't make you that way. So why blame me when I bring it up? Just saying. I didn't do it. Why'd you grow that way? That's a better question. Let's see. I see you there, Joshua. You got some questions. Currently doing an undergraduate project. And I'm working on a thermal solar. Okay. There's ways to do that, similar to an absorption. We are using a flat plate solar collector to gain heat, but it's actually a compressorless system. Yeah, no, I get that. But we are stuck with a particular refrigerant to use. We were thinking of benzene or chloroform. Oh. So Joshua, in your particular circumstance, I think it's a cool project. I think it's a really cool project. I don't have a preference personally. Either direction you go with that. What I would suggest is basically what the approach you're taking is very similar to how we would design a how we would design a absorption chiller. I don't know if you've studied that. I don't know if you're familiar with that. But what I would do is go look at what the fluids they use for those absorbers. And York has some really good published material on their absorption chiller series that you can go. I don't remember the model number of them off the top of my head, but I would go reference their documentation. And if I'm understanding what you're building correctly, you'll find that there are some there's a lot of overlap into what you're trying to build. Now, an absorption chiller, it sounds like you're trying to create something far more simplified. Maybe you're not even trying to use a actual pump. So that would be one question I might have is, are you okay with having a pump? Because you could call a pump a compressor. A compressor is a pump, right? So that term is interchangeable. And yeah, so are you okay with a pump circulating fluid in the system at all, or are you trying to strictly do a basically an induced flow, right? Are you trying to strictly do an induced flow where there is no mechanical action being applied to it? And at that point, are you also using you say a flat plate solar collector to gain heat? Because that's also okay. Another example of this would be the old school propane refrigerators we'd had in RVs. And I'm trying to remember, it was not a mechanical compressor. It was a multi-chamber, basically bulb of in the piping that we would heat with propane. And I've worked on something similar to this. I tried to design my own heat-based compressor and recreate those old propane ones myself. It's a really fun project, I tell you. Man, it's been a long time since I thought about that too. Gosh, that was so long ago. I remember being in the garage trying to put that thing together. Gosh, I'm trying to those compressors that I'm thinking of. Those they had a particular name, but they weren't mechanical. We used propane heat. So in your case, instead of propane, you're trying to utilize solar heat, which using a collector like that, you can then focus that heat into a central point to heat a bulb. You can create a flashing process, which then ends up creating this whole kind of induced draft of refrigerant through the system. I'm pretty confident those old school fridges were R12. I think they were R. Now, obviously, I'm not suggesting you use R12 here. Okay, that's not what I'm saying. But those would be some examples. How did they do those, right? And I would compare, because all of those systems are very successful. They're just niche, and they're not the easiest way to do it, but they're a good starting point for your research, right? So step one is make a working model, right? If you can't make it work with any technology, then like your premise may be flawed in the first place. And let's get to a working premise that actually functions, not on paper, in real life, right? That's a key step there. Then how do we improve this? How do we continue the iteration process to make it what we want it to be? So you want it to be a fully solar generated cooling system. By all means, I think it's going to be hard to do at scale, but at minimum on a smaller scale, like those fridges with a propane. It was a tiny little propane flame. It wasn't much. It didn't take a lot of heat to make those refrigerators work. And you're not trying to do a PTC style, which I think those still have a long way to go. I've had so many ideas on how to convert or how to design a PTC cooler at scale, and maybe even trying to use it in a hydronic sense. But I ran into that same point. I made all kinds of models. I experimented with all kinds of things,
but I never could build a working model was my issue. Now, granted, I was far less experienced then, and I know I made a lot of mistakes with what I was like how I was trying to build it. I would try that again very differently today compared to what I did back then. But yeah, maybe if we got a little more propane. Okay, let's see. Yes, using a pump. Okay, so you're okay with flowing via pump, and you say propane. Oh, I think yes, you're using a pump. Solar-based economizers on the water side. Yes. So what I would say, if you're okay with using a pump, then you're really pushing into the absorption territory. Have you tried to study or look at absorbers? Have y'all included that in your study process or as examples of systems that have worked in the past? I'm just curious. And we're gonna have fun real quick talking with Joshua, and then we'll dive into some more questions. But I think this is a fun project. It's worth a fun discussion. We don't get to have these kind of chats every day. And I'm very much into the R&D thing, right? I spent years like experimenting with designs. I've designed all kinds of stuff to do different things. I've never patented anything. Just never took it that far. It was always just a hobby and just fun goofing around. And if I happen to rediscover the next generation of air conditioning, so be it in the process. But that was never truly the goal. Versus, I have this idea. What happens, right? So this is very much. Very much. Okay, so y'all have looked into absorbers. Okay, so then you'll be familiar with what I'm talking about then. Yeah, to the core of your question on which refrigerant to go with, I don't have a personal opinion there. I really don't. So try both if you have that availability, right? Maybe you don't. I don't even know if you're going to be able to build a working model versus just a theory. But if you could try both, do it. Make one of each and then do a operational comparison. How many BTUs is that system able to process, one compared to the other? How many issues do you run into? Where's the inefficiencies in each? What stage of the process in the cycle are they struggling? Yeah. Again, you may not have that option, but if you did, that's what I would try to do. I would try to build both and then compare them. One may require far more solar heat or solar radiation in order to work correctly than the other does. At that point, that's a benefit, the one that requires less, but then again, if it requires less, does it move less BTUs in total as well? So there's compensations there, like what is your target? Yeah, if you want to follow up Joshua and kind of talk through some of this on the side, it's a really cool project. I'm very into this kind of thing. I love playing with this stuff. All right. Been told by a carrier tech that they purposefully don't put their service ports down low so that they force you to recover in gas phase only, supposedly to avoid siphoning oil into the tanks. And I would say that is true because Carrier is so terrible at oil migration, it's not even funny. Like, they are so bad at migrating oil. Yeah. Yeah. Their evaporator is plumb full of freaking oil all the time. I mean, yeah. Yeah, I'm just not a any reason they'd be scared of oil. I mean, so yeah, so seemed in fairness though, Trane is not that bad at oil migration. Well, okay. All right. Let me take a step back here. I'm thinking of their centrifugal line. Their screw water cooleds are about as bad as carriers are at oil migration. That is absolutely true. Yeah. And their whole gas pump thing works, but I don't know why they wouldn't just do an eductor, personally. Like, just put an eductor in. It simplifies so much of the process. And surely it's not a patent issue. I don't actually know why they're so committed to the gas pump. I really don't. Maybe it's a volume of oil. Maybe they feel like they can't get a high enough high enough volume of oil through the eductor compared to the gas pump. That could be, I could see that argument. Or maybe they find that the eductor is less efficient because it's constantly pushing through. I don't know. They've probably got some kind of reason as to why. I would assume they would, and it wouldn't be just a patent problem. But you're right. Yeah, Train didn't care. So in terms of why they're they want to keep the oil in the system. They don't want you to pull the oil out and then not have enough oil in it in the first place. A lot of people don't know oil separation practices, or, well, it'd be faster to do oil separation in a tank. But again, a lot of guys don't know how to manage oil in the recovery cylinders effectively. Like, that is part of our issue, is knowing how to manage that process of, okay, I know I should have X amount of charge. The last little bit of charge, or the last tank of refrigerant I pulled out, is going to be heavily oil latent, right? All those kind of variables. What does that look like when we have to then separate that oil outside of the chiller, and then we have to dispose of that oil? That also means we have to add oil back into the chiller at that point. Having the oil pulled from the machine can create a lot of issues, especially for carriers machines that already severely struggle with maintaining oil in the first place. So I could see why they want to push for it. I just don't like it, right? I'd much rather just be able to manage it myself. But that's not what they do. So, okay, CVAs. Yeah, experience-based resolution, yeah. If you have 2 or more chillers in parallel, shouldn't each one have a obligatory water check valve on its outlet? So some installers don't seem to accept the mandatory character of it. Yeah, so if you're running parallels like that, yes, you have to, either there'll be a check valve, or there's usually a check valve at the pump outlet, and many times it's built into the pump skid, right? Or built into the pump assembly. The pump will have a check valve at its outlet. That is rare to see it not. I'll say it that way. But beyond that, many times the chiller itself will have a actuated isolation valve. So you could see it either way. You could either have just a check valve, you could have the isolation valve that's on an actuator, or you could have both. If you're dealing with a common headered system, you'll usually have an actuated butterfly valve, usually butterflies. You'll have that on at least the entering side or the leaving side. I mean, the leaving side of the chiller will have that actuated valve on it. Now, in a primary scenario like that, you will have a check valve at the pump almost always. Now, does that mean the installers actually put one in? No. If they don't, will that chiller become a bypass for the rest of the loop? Yes. Is that okay? Not in my opinion, but yeah. Yes. So if you're in parallel, you should have a check valve, at least at the pump. At least. Yeah. Mr. Freeze. New plant, ground floor up. What are the proper colors for chilled and condenser water loops, potable water, fire pipes, glycol loops? Yeah. This is a really good question. And I can actually pull a chart for this, but we'll start with just a basic answer. Okay. Shrink that down a little bit. New plant, ground floor up. What are the proper colors for chilled and condenser loops and potable water, fire pipes, glycol loops? So usually for condenser water at minimum will almost always be green. Okay. So this will be green for condenser water at a minimum. This is usually not insulated. Many times the chill water loop will be insulated, and it will depend on the plant. In some plants, they may paint the chill water green as well. In other plants, they might paint it blue. All right, so you'll have either a single color or two shades of blue. So chilled water, and this is non-potable. So both of these are non-potable, by the way. Chilled water will sometimes be blue and or green. Now, if memory serves, potable water is actually supposed to be blue, I think, or compressed air is blue. We'll come back to that in a second. So I will tell you though, if you see chill water pipes painted blue per like mechanical code standards, it's technically wrong. Now, most all of us understand what we're looking at, and it doesn't become an issue, but it's technically wrong. Now, fire is going to be red. And that's something to keep in mind is if you have what they call a tri-water loop where your fire and condenser water are in the same, then I think they still label that as red because it is still your fire system just tied into your condenser water loop. So if you do see a condenser loop that has red piping, it might be a tri-water loop. And this is one reason why, well, that also gets back to branding. I'm not going to say that. Okay. So condensed water is almost always green. Chilled water is going to be a lot of times blue, but it'll be the insulation itself that's painted, not the physical pipe because the pipe's covered up. Or the chill water could be green. Your fire is going to be red. Glycol loops where it's like pure glycol flowing through them. I don't know what that color would be. Potable water. So we have potable. I think potable may be brown. And I think compressed air is blue. So we can look this up. Let's do this. Let's see. Plant. Or mechanical pipe colors. How about that? Mechanical pipe colors. Yes, here we go. So, yeah, sprinkler water which is fire, is red.
Yeah, compressed air is blue. That's right. Boiler or condenser water is green. And there is a difference between potable and non-potable water on the codes. Let's see what this one. Let's just go back. Look at Sherwin-Williams site. Let's see what they say. I don't want your cookies. No, thank you. All right, so finished or potable water, they recommend it using a dark blue, which is what I remember. Yeah, raw water or non-potable. So raw meaning non-potable is green. Let's see. Stationary sewage, sludge. Anyway, we could read through this ad nauseum, I guess. Compressed air. So this one shows compressed air is green, but I don't. That's not what I'm used to seeing. I don't usually see that as green. Anyway, I think part of the point there is it does fluctuate depending on where you're at, what plant you're in. But in terms of your general question, it's very common that blue will be used for like compressed air. I've seen that. It can be. I've seen blue and I feel like brown. I've seen both blue and brown used for potable water. And then yeah, your non-potable is typically going to be green, or like I said, chill water. It'll be sometimes blue. Let's see. Let me catch up on the chat here. It got cold. It got narrow. Gosh. Guys. Carrier 30XB, 600 ton. It's giving error. Under volt 1. Cannot be cleared. This error occurred after boards A and B were swapped. So that's going to be a was it Donic? It's going to be an addressing issue. So Carrier does addressing on their modules. And this is just me pulling off of memory without actually looking it up in the book. That should be an address problem. When you see that it's reading the wrong address for the module probably needs to be readdressed for whatever you're troubleshooting. So if you're trying to do a board swap as part of your troubleshooting process, look at the little dip switches. That's usually where they'll control the addressing on the module, and you'll need to set the address correctly on that module to then swap it between the two. I'm pretty confident that's what you're seeing there, without some extra feedback. With absorber, you need a rate of heat added. Yep. Sun, like 300 square foot or something like that. Absorber is good where waste heat. That was your right. When charging back system, I heat up the recovery tank so much there's no way for oil to stay in. Way too hot on there. When charging back the system. Oh yeah, so you heat up the tank so that the oil gets thinner to help get the oil back out.
I mean, like you said, you heat it up a lot. You have to get that tank pretty freaking hot for that. But that goes back to that's if you're doing a vapor charge versus if you're charging back liquid, the oil is just going to get drawn out with the liquid. If you're charging back via vapor, which I'm trying to think of a scenario that you would charge back vapor to something. At least vapor on a chiller. Let me rephrase. Like in a chiller conversation, when would I charge vapor? I can't. Like if I have oil, I need to, or not oil. If I have liquid refrigerant, I need to move. I can't think of when I would want to charge vapor. Yeah. Yeah, I'm curious there then, Sterling. And charge back liquid. Oh yeah. Yeah, well, you don't even have to heat it if you're charging back liquid. Yeah, I was just trying to think of a situation where I would do it that way. But if you're charging back liquid, like heating it doesn't even it's gonna flow out with the liquid refrigerant anyway in the dip tube. Or at least it should. So to your point though, so those liquid dip tubes don't go all the way to the bottom perfectly. And so, to your point, which I'm trying to think if heating it would even help with that because the oil is going to sit on top of the refrigerant. It has a lower specific gravity. So because of that, the last like inch or half an inch or whatever at the bottom of the drum would end up being the trapped oil, and we can't boil that oil out of there. The only way to get it out is to dump it out of the tank. So to your point, you get the tank really hot to try to draw it up the tube, up the liquid tube. But even then, I'm trying to think how would making the tank hot get the oil to go up the tube when the tube doesn't technically go to the bottom. Like when I say that, I mean it stops like a quarter inch or half an inch shy of the actual bottom of the drum. So I'm just trying to think. Have you tried taking a tank like that had a heavy oil charge and dump it out? The tank got hot, high pressure, oil can't stay in. Flip the tank upside. Okay, a few times. Use the gas port upside. Okay, all right. Yeah, not questioning your methods here. I'm just trying to understand. But yeah, so if you're flipping the tank, then you're actually seeing what oil's got left behind. That's an interesting thing. I haven't done that. I haven't heated the tank like that in order to try to push or draw the oil out of it. In that regard, just never thought of it. I haven't seen anybody else do it. It's an interesting thought. What's the most issue that happened in York water-cooled? Surging. If we're talking about a York centrifugal, surging. Like the number one thing I deal with York water-cooled is surging. Okay, Donick. After the undervolt error, we checked all the electronic components. There was no problem. We also replaced power supply board. The error does not go away. Yeah, so I go back to address of the board. If that's even an issue, that particular one may not. And then I don't remember which controller, if that's the older style with the comfort or if that's the newer style with the little touchpad. So I don't remember which controller is going to be in that or which vintage of machine you have. But some of those are auto clear, right? So and the manual should tell you, because when it's an auto clear, it doesn't really matter how, like there is no way to reset it. resetting it doesn't do anything. It just going to immediately come back and re-trigger. Especially on those undervolt ones like that. So if it's a manual clearing and if it's a newer controller, have you signed in via the carrier app? What is the Comfort Link or whatever their app is? I don't remember the name of it offhand. Have you logged in and gotten the service login for that machine so that you can do a reset on the password? So have you gone through that process? If you haven't, then you'll need to get that app and get the service code, and that's if it's the newer graphical interface. If it's the older one, then like you should be able to clear it. You'll have to put the service password in, which on those is 111 or 333. One of those two should allow you to reset the alarm if it's the older style marquee display, I think as they called it. You guys color code your pipes, eh? Yes. Here, most have stupid rounded sheet metal that attach. But correct me if I'm wrong, Sterling, y'all are in such a climate, like y'all have freezing winters. So here's something we will do. If we don't paint, like, so if we have jacketing, that's what, when we have that that sheet metal aluminum coating on the pipes, we call that jacketing, at least in my area. And when we have jacketing on it, we typically won't paint the jacketing, but what we will do is we'll put a zip-tied label, and those labels will still be color-coded accordingly. So it'll have written on it condenser water, chilled water, potable water, whatever. That will still be there, but the color code will still be accurate, and it'll have it written in text, and we just zip tie that. Or sometimes they're a sticker. They won't zip tie. They'll sticker onto the jacketing, right? But y'all are also in a climate where you'll need a so I'm down in the south of North America, so we don't have the same kind of winters that y'all have there. You're much further up into the hemisphere. So I know guys who are in the northern states here deal with a lot more insulation and jacketing and stuff than what I have to deal with in my region. Also because these stupid gas laws. We need to give back recovery tanks empty or with next to nothing left. Otherwise, if too much left... yeah, we don't have any of that stuff. Yeah, we don't have that stuff at all. People turn in tanks with bad refrigerant and stuff all the time. There's no questions. You turn it into a receiving center, whoever that is, and they deal with it. And if it comes in with trash refrigerant, like from a burnout or something, like they'll charge you extra fees, but there ain't no paperwork to do with it. Is there a way to calibrate the HMI on a Centrovac? As in the displays? Yes. Yeah, there is a screen calibration, and you activate it, and you have to touch the corners or something to that effect. It's been a while since I've ever needed to do that. But yeah, there is it's in these settings menus somewhere in there. There's a screen calibration button. That's on the newer TU controller. So if you open the control cabinet, you got a little white controller in there, and in the bottom right or left corner, it'll be a little white automation looking controller. That's it's a UC control module. So that's the ones that use the actual fancy touchscreen graphic for the HMI. If it is the older style, Okay, so if it's the CH530, those do not have calibration. Those just have to be replaced. I'm pretty confident. I don't. So the CH530 ones had a green screen, and I don't have mine. I have a example of this, but I think I've got it put up in the shed. I need to pull that out. Those do not have a calibration, if I remember correctly. I could be wrong on that. But those will get like way the heck out of. You'll touch here, and 2 inches over, it'll click a button. Right? It's an ever-loving pain. That's just replacement. When you have one do that, I've always just had to replace the screen module, the HMI itself, and that got it fixed. It's ridiculous. I got stickers around the jacketing where I'm at also. Arrows showing direction full. Yeah. They have stickers too, but not necessarily color coded. No, that's interesting. Correction. We have recovery tanks, which are for destruction, recycling, and transfer tanks, which are for reusing in this system. Ah. Yeah, we don't have that. It doesn't matter where I'm at. You just stick the refrigerant in and pull it out, and if it's bad, take it to somebody and drop it off. That's about it. I haven't been able to find the screen calibrate. It's the newer ones, I believe. Okay. And like I said, I could be wrong on this groove. I remember it being in the settings menu. I don't remember where. I wouldn't, without looking at it, I wouldn't be able to necessarily guide you to it. But I do remember it being there. I've got the HMI like operator's manual for that screen. Send me an email and let's follow up on this after the fact. So that's hvactime@hvactimetx.com. Send me an email. I can send you that manual, and I can even just look it up after the stream here. I do need to wrap it up. I can look it up in the stream after the stream and see if it says in there how to do it. I've got a distinct memory of there being one. I really feel like there is one to where you can calibrate the touchscreen. I'm just not clicking as to exactly how to get there. Of the touchscreen, I'm not sure if there is a fix besides replacing it. Yeah. Different paperwork and cannot be used. Use recovery tanks for recharge under any set. Yeah. Seem the adaptive view controllers lose calibration. Not really cleaned. The transfer tanks are supposed to be cleaned and under vacuum. That's interesting, Sterling. Okay. I gotta wrap up, guys. MTT. Make the time for your family, for your spouse, for your kids. It's a very difficult, busy career. We have a lot going on. We're in high demand. We will be for some time. This is not going to slow down for us anytime soon. There's not enough of us. What that also means, though, is we have to make the time for our family. The time's not going to be there. We have to create it. We have to intentionally make it so that we can give them the time they deserve to. It's a struggle. We have to provide. It's going to require a lot of us to do that. At the same time, if we don't at least try to be intentional with that time with them, what's it all for in the end anyway, right? Anyway, MTT, I will see y'all later. Have a great week. I won't see you next week. I'll be hosting the hands-on class